Hello and welcome back to some more Stiffness Method solutions in structural engineering. So today what I thought would be helpful would be to solve an exam style question. So until now we've gone through all the theory, we've solved questions, we've done some coding, but what happens in exam conditions when you don't have MATLAB and you can't use that? So let's solve a question probably for around year 3 to 4 in the UK university system from start to finish. We'll go slow, we'll understand everything, but if you need any recap on the theory, go back to the lectures. So this is the question we're going to solve. We have a fixed support at A, we have a roller support at B, and we have a point load at C of 10 kilonewtons. We need to find the reactions using the stiffness method. Now, a few things to note here. The first thing, EI is going to be constant throughout. That's noted in the question. The second thing to consider is that this beam is axially rigid, meaning there are no axial deformations, and we can use the smaller stiffness matrix for the beam, the 4-on-4, instead of the full 6x6, which includes axial deformation. Let's get to it. So, as we said, we have this beam. We can see that the beam is horizontal. There are no angles here, and luckily for us, the local coordinate system coincides with the global coordinate system, that is xy. The next thing I'm going to do is I'm going to number my degrees of freedom. So since we don't have any axial degrees of freedom, I'll have degrees of freedom 1, 2 here, 3, 4 here, and 5, 6 here. If I want to draw them out, they will look like V1, theta 1, V2, theta 2, and V3, theta 3. Those are all my degrees of freedom. Now, in order to solve it, the first thing I'll do is I will label this element 1 and this element 2, and I will start out by writing the stiffness matrices for each beam. So starting off with element 1, call that K1, small k because it is in the beam, and I'm going to have a 4x4, and I'm going to have here 12 over L1 cubed, 6 over L1 squared, minus 12 over L1 cubed, and 6 over L1 squared. Here, 6 over L1 squared, 4 over L1, minus 6 over L1 squared, 2 over L1, minus 12 over L1 cubed, minus 6 over L1 squared, 12 over L1 cubed, minus 6 over L1 squared, and the last line, 6 over L1 squared, 2 over L1, minus 6 over L1 squared, and 4 over L1. All of this obviously times by EI, and noting that L1 equals 10 meters. Quick check to make sure that everything is symmetric and I've not messed up any of these. Now, one more thing before I move on to element 2 is I want to put the labels of what degree of freedom in the global coordinate system this relates to. So I've got 1, 2, 3, and 4, and 1, 2, 3, and 4. I'm going to move on now to doing exactly the same thing for element 2. So K2 equals, and then if I open my brackets, I'm going to have exactly the same thing, just with L2 instead of L1. And once again, all that times EI, and here L2 equals 5 meters. And once again, I'm going to note the degrees of freedom. Now we can see that element 2 has degrees of freedom 3, 4, 5, 6. And so that is what I'm going to note here. So 3, 4, 5, 6, 3, 4, 5, 6. Now that we have the two stiffness matrices, and noting that there is no need to rotate, as they are already in global coordinate systems, we need to now assemble the full stiffness matrix. So the full stiffness matrix, K, is going to be EI times a matrix of 6 by 6. And in this 6 by 6 matrix, it's going to go according to the degrees of freedom. Now I know that my full matrix is going to be a matrix of 6 by 6, right? Because I have 6 degrees of freedom in total. And what will happen is the matrix for element 1, which is aligned to degrees of freedom 1 to 4, is going to slot in that bit here. So 1 to 4, so just here. And then the stiffness matrix for element 2 slots in for places 3 to 6. And that is why numbering makes seeing this very, very easy. I'm not going to write out each stiffness matrix here because that would just be copying again. But the important thing is where there's an overlap, so in this area here, this is where I will add on. So for example, in this place here, global K33, I am going to add on this one here from element 1, 3, 3, and this one here from element 2, which is also 3, 3. So they'll get added on. But I'm only going to actually write out the things that I need. Now we obviously know, because we study the stiffness matrix method, that the equation is K, the stiffness matrix, times the vector for displacements equals the vector for force. And that is for the full system. So if I draw that out, I have in my case EI times the full matrix times the displacement vector, so V1, theta 1, V2, theta 2, V3, theta 3, and that equals the force vector, okay, so F1, F2, M2, F3, M3. Now we do know the force vector because this is all the external loads, and actually if we go back up to our beam, we can see that only at the location of degree of freedom 5 or F3 we have a force, and that is 10 in the negative direction, so it's minus 10. So really what we have is zeros apart from here where we have minus 10. So just fill those up. And that is our external force vector. Let's just add also the degrees of freedom here. So 1, 2, 3, 4, 5, and 6. Now I don't need to solve this full system because I know that degrees of freedom 1, 2, and 3 are restrained, right? So at those restrained degrees of freedom, there will be no displacements or rotations developing. So I can get rid of everything that has to do with degrees of freedom 1, 2, 3 to get my reduced system. And if you need a reminder of that, just go back to the lectures. So row 1, row 2, and row 3, and also column 1, column 2, and column 3. And what I'm left with is the reduced system. If you can recall that from the lectures, that is KFF times DF, so the free displacements and rotations, and that equals FF. This, what is left here, this bit of the matrix is KFF, this bit here is DF, and this bit here, which is also the same as this bit here, is FF. And that is what I need to solve. So let's write out the reduced system fully. So the reduced system is going to be EI times this stiffness matrix, which will have degrees of freedom 4, 5, and 6 only, times the displacements and rotations, so theta 2, V3, and theta 3. These are all the degrees of freedom that are free to move and rotate, and that equals the force vector, which we already established was 0, minus 10, and 0. And so now we just need to populate the stiffness matrix. So as you can see here, we need to take from that first matrix the bits that are related to degrees of freedom 4, 5, 6. So really it is just this element. And from the second matrix we need to take 4, 5, 6 as well. So it is this part of the matrix that we'll need to bring over. So let's do that, and let's also put in the relevant L's. So from matrix 1 I have here 4 over 10, and from matrix 2 I have another 4 over 5. The rest is now just from element 2, so minus 6 over 5 squared, 2 over 5. Here I've got minus 6 over 5 squared. Here I've got plus 12 over 5 cubed, minus 6 over 5 squared, and to finish off, 2 over 5, minus 6 over 5 squared, and 4 over 5. And that is the reduced system that I need to solve to get the displacements. This gives us 3 simultaneous equations. Let's write them out. Okay, so equation 1 is from that first row, so I have EI times 4 over 10 plus 4 over 5 times theta 2 minus 6 EI over 5 squared times V3 plus 2 over 5 EI times theta 3 equals 0. From the second row I get minus 6 EI over 5 squared times theta 2 plus 12 over 5 cubed EI times V3 and minus 6 over 5 squared EI times theta 3 equals minus 10. And my third equation is 2 over 5 EI theta 2 minus 6 over 5 squared EI V3 and plus 4 over 5 EI times theta 3 equals 0. So now I need to solve 3 simultaneous equations. I'll do that here explicitly, but obviously if you have other methods, you're welcome to use them. So the first thing I'm going to do is I'm just going to divide by EI, the first equation, the third equation, and also the second equation. Just in the second equation I do need to remember to divide the minus 10 by EI. Now I'm going to subtract equation 3 from equation 1. And so doing that, here I've got 6 over 5. So that gives me 4 over 5 theta 2 minus 2 over 5 theta 3. Because in both cases I have minus 6 over 5 squared EI times V3. So that equals 0. And from here I get that 2 theta 2 equals theta 3. Sub into equation 1. So just taking that 2 theta 2 equals theta 3, subbing that into equation 1, and I get 6 over 5 theta 2 minus 6 over 25 V3 plus 2 over 5, and now times 2 theta 2 equals 0. That gives me 10 over 5 theta 2 minus 6 over 25 V3 equals 0. So 2 theta 2 equals 6 over 25 V3, and V3 equals 50 over 6 theta 2. So you can see that what I've tried to do is express both theta 3 and V3 in terms of theta 2, and now I can sub them both back into equation 2 and find out what theta 2 is. So sub both relationships into equation 2. And so here I get minus 6 over 25 theta 2 plus 12 over 125 times 50 over 6 theta 2, and minus 6 over 25 times 2 theta 2 equals minus 10 over EI. And if I solve that, I've got 2 over 25 theta 2 equals minus 10 over EI, and I'll find that theta 2 equals minus 125 over EI. And if I just bring it back, I can find that theta 3 was 2 theta 2, so that gives me minus 250 over EI, and V3 was 50 over 6 times theta 2, and that gives me, if I calculate it, minus 1041.67 over EI. But that is not the end, because what I've been asked to do is find the reactions. So let us remind ourselves how we do that. So to find the reactions, we need to go back and look at global equilibrium. And if we go back to lecture 8, where we discussed all of this, we will remember that we could separate our stiffness matrix into the restrained and free degrees of freedom, and we got this division. Okay, and this is just to make our life a little bit easier and to solve less of the matrix, especially useful in exam conditions. So this was the full stiffness matrix, but we also noted in lecture 8 that when support displacements are 0 and there are no external forces at the restraints, the reaction vector equals KRF times DF. Now, we have just found this. We know this because this is part of the stiffness matrix, and we already know the full stiffness matrix. So we will be able to find the reactions, what we're looking for. Before we do that, let's just go back to our drawing of the stiffness matrix and highlight what KRF is. So going back through all our calculations, back to here where we drew everything out, this part here in which the rows were restrained but not the columns, this bit here, that is what we're looking for. That is KRF. And so we can see here that KRF is a 3-on-3 matrix, which makes sense because it is NR, the restrained degrees, which is 3, on NF, which is also 3, the free degrees of freedom. And we can see here that it is the columns 4, 5, 6 and the rows 1, 2, 3. Let's write that down clearly. So the size of it has to be NR on NF. NR, 3 restrained degrees of freedom, free degrees of freedom. So it's a 3-on-3 matrix. And we've just looked and found out that we will have degrees of freedom 4, 5, 6, and 1, 2, and 3. And that is KRF. Okay, so let's fill this in. So obviously we have EI multiplied by this. This gets multiplied by the degrees of freedom, which we just found. So we have here theta 2, V3, and theta 3. We just found these, we know them. And that will give us the reaction vector, which if we open it up will be the force at degree of freedom 1, the moment at degree of freedom 1, and then the force at degree of freedom 2. Okay, so these ones here, 2, 3, and 3, they correspond with this, and these ones here correspond with these degrees of freedom here. So let's have a look what we need from the 2 stiffness matrices from each element. So for this, we need column 4 and rows 1, 2, and 3. So here, let's just use a different color to show that. So column 4, rows 1, 2, 3 gives us these. And from element 2, we just get this row here. So that is what needs to be taken into account. Let's write that out explicitly now. Here I have from element 1, 6 over 10 squared, 2 over 10, and minus 6 over 10 squared. And the other things come from that row in element 2. So here I have plus 6 over 5 squared. Here I have minus 12 over 5 cubed. And here I have 6 over 5 squared. And the rest of these are just zeros. So once again, we have 3 equations to solve, and we will find those reactions. So starting off with the first one, F1 equals 6 EI divided by 10 squared times theta 2, and that is 6EI over 10 squared times minus 125 over EI, which we found. Obviously, EI and EI cancel each other out, and we are left with minus 7.5 kilonewtons. Moving on to the moment at degree of freedom 2, or M1, we have 2EI over 10 times theta 2. That gives me 2EI over 10 times, once again, minus 125 over EI, and again, EI and EI cancel each other out, and I'm left here with minus 25 kilonewton meters. And the last one we need to solve is F2. So that is the reaction at the roller at point B. And this is a bit more complicated because I have a few more things here. So I've got minus 6 over 10 squared times EI plus 6 over 5 squared, also times EI, and that is timed by theta 2. And then I've got minus 12 EI over 5 cubed times V3, and then I've got plus 6 over 5 squared times EI times theta 3, and now I just need to substitute everything in. So if I do that, I get, let's see, 9 EI over 50 times minus 125 over EI. Then I have minus 12 over 5 cubed EI times minus 1041.67 over EI, and I also have plus 6 EI over 5 squared times minus 250 over EI, and that gives me, if I calculate it and cancel out the EIs, minus 22.5 plus 100 and minus 60, and that gives me 17.5 kilonewtons. And that's it. We have found all the reactions. So F1 minus 7.5, M1 minus 25, and F2 17.5. But just before we finish up, let's draw out our beam. Okay, this was what we had, 5 meters, 10 meters. And let's put all of these in their direct orientations and do a little check. So here I got 17.5 kilonewtons. Here I got, because it was negative 7.5 kilonewtons in this direction, and also negative, so this is the direction of the moment, 25 kilonewton meters. And a good way to finish a test would be just to do a very, very quick check. So let's do that. So let's check by summing up all the moments around A and hope they all add up to 0. So we've got minus 10 times 15. That is the point load. Then we have plus 17.5 times 10. That is the reaction at B. And then we have minus 25. That is the concentrated moment at A. And all of that does add up to 0. So it's a good check just to make sure that we're on the right track and we've solved correctly. And that is us. We have found all the reactions for this beam using the stiffness method. And there you have it. We've managed to solve an exam-style stiffness method question. As you can see, it is quite long and procedural, but we did take time to explain everything. So with practice, this will get much, much shorter. And obviously you can take some shortcuts. You don't need to draw everything out. I just wanted to make it very, very clear what we were doing. I would expect in a question to have probably a maximum of 3 simultaneous equations. So you can see you're quite restricted to how many degrees of freedom there can be in an exam. Probably something around 6 or 8, depending also if you need to spend time rotating those matrices and how many boundary conditions you have, because that will limit how many equations you solve. But that's it. See you later for some more stiffness method questions.